Okay, let's talk about the electrical driving force. The electrical driving force. So the electrical driving force is dependent upon the charge of a particle as well as the polarity across the cell membrane. I'm going to explain what that means. So we know that an ion is a charged particle, such as sodium, chloride, potassium, so on and so forth. And a cation has a positive charge, such as sodium, whereas an anion is a particle with a negative charge, such as chloride. Okay, now depending on whether it's a cation or an anion will determine the electrical driving force. Right? Depending on the charge of that certain particle in question. Also, there is the membrane potential. The membrane potential. Does anyone know what the membrane potential is? Can anyone describe what the membrane potential is? It's a very, very important concept. We're going to talk about this a lot, particularly when we talk about the action potential. So this is a force that is caused by the unequal distribution of charge across a membrane. All right, what does that mean? That means if you have a cell membrane, right, and you have more cations on the outside of the cell membrane and more anions on the inside of the cell membrane, the anions, they're going to want to attract, right? Negatives attract and lights repel. So separating that charge across the membrane creates a force, creates an energy. And if you think about it, this is how a battery works, right? The separation of that charge. I'll say that again. So you have a cell membrane, you have more anions, let's say inside the cell, making inside more negative. You have more cations outside the cell, making outside more positive. The separation of this charge creates a force by which these particles want to cross that membrane. That is called a membrane potential. Right? That is the energy or the stored potential that is created by an unequal distribution of charge, which is present by an unequal amount of cations or an unequal charge of cations across the membrane. Okay? Any questions on that? Okay, so having a membrane potential along with the charge of the particle in question, these are the two factors that create the electrical driving force. Okay? These are the two factors that are important for the electrical driving force. The polarity or the charge across that cell along with the charge of the particle in question. Now the magnitude or the strength of the membrane potential is usually measured in millivolts. Millivolts, it's usually indicated by Vm, which you see here. And it's usually referencing the intracellular fluid compartment. All right, what does that mean? So if I have a cell and there are more anions inside the cell, you guys have questions? No? And there are more anions inside the cell, more cations outside the cell, the magnitude of the membrane potential is going to be referencing the inside of the cell. So it'll be negative if there are more anions in the cell. Okay? And so this polarity is what we mean when we say the separation of charge. So if we take a traditional cell at rest, inside the cell is more negative than outside the cell. Does anyone know what the resting membrane potential of a cell is? Negative 70 millivolts, right? And what does that negative 70 mean in terms of what we just said? Who can explain what that negative 70 actually translates to mean? Anyone? What does that negative 70 millivolts mean?
I mean the cell is equilibrium at rest.
Okay, so that's what's happening at rest. What does it mean in terms of the particles across the membrane? What does that negative 70 mean? it means that there's more negative charge in the cell, right? And more positive charge outside the cell. So this creates a negative environment inside the cell, and that is the membrane potential, right? So things are going to want to move, or anions are going to want to move from the inside of the cell to the outside of the cell, and that's the electrical driving force that's created. Okay, let's look at the scenario here. So we have intracellular fluid on the left, in this pink color, and extracellular fluid on the right in this blue. And just as we described a minute ago, there are excess anions on the intracellular side. So inside the cell, there's an excess of anions. What's an example of an anion? Chloride, right? Chloride is an anion, right? So it's in excess inside the cell. Whereas in the extracellular fluid outside the cell membrane, there are excess cations. And so just like a battery, the separation of this charge, which we see illustrated here, creates the membrane potential, creates some stored energy, where particles are going to want to move across this membrane. Okay, that is the electrical driving force. Right? This is very important for you to understand. Any questions on this? Any questions on this? So that unequal distribution of charge across this membrane is what creates the stored energy that is the membrane potential. Alrighty, so principles that dictate the electrical driving force are basically opposites attract, right? Opposites attract, whereas like charges repel. Right? This is something we should know from high school physics, sorry. Opposite charges are going to attract. So if you have more negative inside the cell, more positive outside the cell, there's going to be a force that wants to move across the membrane to go to the opposite charge. Whereas if you had positive inside and outside the cell, nothing would want to move. There would be no electrical force here. Okay, that's the importance of having ions in different concentration, in different charges across the membrane to generate that energy, to generate that differential charge. Okay. Now it's also dependent on the polarity of the cell. The polarity of the cell as well as the charge on that particle. If we're talking about sodium, sodium is what type of ion? It's a cation, right? It's a cation. So the charge on that individual particle as well as the polarity. Is it more negative inside the cell? Is it more positive inside the cell? And this can change. Resting, we said the inside of the cell is more negative, but when a cell, for example, a neuron is excited, the inside of it becomes more positive, right? So that can change. So the polarity of the cell, along with the charge on the particle in question, is what determines the direction or the direction of movement of that particle. Any question, Ryan?
You said opposites attract and like repel.
Mm-hmm.
I guess I'm just not understanding this. Maybe it's a little bit off topic, but like when you talk about the possible bit bilayer, like water, it's polar, and then the polar heads they attract. But in this knowledge, you're saying with electricity, it's off.
Right. So this is dependent on the charge, specifically of ions. Whether it's a cation and they're more in excess inside the cell, or if it's an anion and they're more in excess outside the cell, that's what we talk about with polarity. So if we go back to this scenario, we're talking only about the charge, not the concentration. Right? For the chemical driving force, we were talking about the concentration of certain particles, whether they were more or whether they were less, right? And that was a more visual force. Here, we're talking about the charge of certain ions and their unequal distribution. So if we have more anions, which are negatively charged inside the cell, and we have more cations, which are positively charged outside the cell, that separation that unequal distribution and that separation of charge creates that driving force, where things want to move to the opposite charge. Does that make sense?
Yes.
Right. So in this scenario here again, let's say we had one of these anions with chloride. Right? Chloride now wants to go across this membrane to the area where there are excess cations. Right? That's the force that has been created by separating this charge. Does that make sense?
Yeah, I guess this was a differentiating. When you said like on the chemical one, where you got a polar head attracts to a polar head.
The chemical driving force?
Yeah, like water, it's a polar molecule, but the phospholipid polar head is polar, so they both attract. So it was kind of
they don't attract. So water crosses the membrane.
But I mean, it doesn't repel, I guess.
Right. It doesn't repel it though. Hope that answers your question.
Huh?
Does that answer?
Yeah, it does.
Okay. Any other questions? So don't confuse the structure of the phospholipid bilayer, right? The things that can move. We're talking about things that can move across this bilayer here. Ready? All right, so let's talk about the electrical driving force here. Okay, so oops, sorry. All right, so the electrical driving force, we said that the direction of movement here is determined by 1, the charge on the particle in question. Right? And 2, the polarity of the cell. Right? Whether it's positive or negative. And just for reference, we said that at rest, the inside of the cell is more negative, whereas if the cell is excited, the inside of the cell is more positive. So depending on the polarity of that cell, as well as the charge on the particle that we're talking about. Okay, so let's look at a scenario here. So we'll take a resting cell, and we'll take an excited cell. Okay. Oops, I'm sorry. Let me turn it off. I'm still looking at the screen. May have to show another screen. You can see another one? Okay. Hopefully. All right, I'm sorry about that. Okay, so now we're going to talk about 2 ions. We'll talk about, oops, actually, yeah, let's talk about sodium. Sodium as our cation, and then we'll talk about chloride as our anion. Okay. Now at rest, we said that there's more negative inside the cell than there is positive. So we got lots of negative, and there's less negative outside the cell. All right, so there's fewer positive, and outside the cell, there is an excess of cations, right? In this case, sodium. Okay. Now the reverse is true, we said, for an excited cell. For an excited cell, the inside of the cell becomes much more positive. There's an excess of cations inside the cell and fewer cations outside the cell. And then there's an abundance of anions outside the cell. And then very few anions inside the cell. Okay? So this is what we mean when we say the electrical driving force. All right, this unequal distribution of charge across the membrane here. This creates a force where these particles want to move across the membrane. Okay? When we let's take a resting cell. Let's look at sodium. Right? Sodium is in a higher concentration outside the cell, and as a result, it wants to move inside the cell. Okay? So it wants to go from an area where it's positive, mostly positive, to an area where it's mostly negative. Those opposite charges are going to attract each other. And the reverse is true. Chloride, let's take chloride here, wants to move outside the cell. Okay? Let's take the opposite. Let's take the excited cell. Now, where is chloride in higher concentration? It's going to be outside, right? So as a result, chloride here wants to move into the cell along its electrical gradient, and sodium wants to move out of the cell. Put sodium here, along its electrical gradient. Okay. Everyone understand that? Can everyone see that? Right? So that's the chemical force, which we talked about earlier. This is the electrical driving force. This is the electrical driving force. And again, this is based on the charge of that individual particle. Is it an anion? Is it a cation? As well as the polarity of the cell. Is the cell resting such that it has a higher concentration or a higher abundance of anions inside the cell versus excited? When it's excited, there's an excess of cations inside the cell. Okay, so those two things determine the electrical driving force.